Okay, everybody. So the idea is to have this lecture series this week with 4 lectures. Today, tomorrow, Wednesday, and Thursday from 2 to 4. Well, to the speaker, right? On this mini course, right? So the title of the mini course is Introduction to Optimization and Operator Theory. It's a pleasure to have Professor Anteneh Gebrie here from the Gebrie University in Ethiopia. So this is part of the ICTP SIMPA Research in Pairs program. Okay. So you have the floor, Anteneh. It's a pleasure to have you here.
Okay, thank you for your introduction. First, I would like to start saying thank you, SIMPA and ICTP, for giving me this opportunity for research collaboration and to have such kind of approach delivery. So my discussion will be on introduction to optimization theory and further. So I'm going to have a discussion on optimization and operator theory. So this kind of introduction. So in the first lecture, that is today, I will have a discussion on introduction for my next 3 lectures. So it is basically on differentiability. We'll discuss here graphics differentiability, agents, and the properties also. And in the next discussion, maybe tomorrow, in our Morrow's discussion, we'll discuss about Fenchel duality. So in the same discussion, after discussing about Fenchel duality, I will discuss on duality and optimization. Then these all discussions are in normal space. Makes it complicated when considering space to be Hilbert space for 5-dimensional space. Where discussing duality is different. Then the third one, because I'm going to discuss about numerical results, we'll have numerical optimization. Some examples of numerical optimizations. I will discuss this in the Hilbert space, almost developing algorithm or numerical method in kind of normal space. Complicated. I will try to see some classical optimization algorithms like proximal point algorithm, forward, backward algorithm, dash-forward algorithm. We will see some classical algorithms in here. So let me start my this discussion. Before going to directly differentiability, let me set what is the center of my discussion. The center of my discussion. The center of my discussion is optimization problem. Let me put the very simple standard of optimization problem. Very simple standard optimization problem is finding X bar subset of X, subset of C, subset of X. X is non-bit set, but that the value of f of X is the increment of over this term, where the function f is maps from X to R plus during this length. So X may be any set. X may be any set. So if we have a function f, this is a very simple standard optimization problem. Very simple standard optimization problem. So having this standard optimization problem, many researchers or many researchers have been done based on this problem. Maybe optimization problems are based on the function f. There is a constraint c. This constraint c, maybe it is a solution of a certain problem. It may be a solution of a certain problem. It is constrained if C is not the whole space X. If C is the whole space X, it will be unconstrained problem. So this optimization problem is divided maybe based on the characteristic of F or C, so that sometimes we have discussion of smooth optimization, non-smooth optimization, linear optimization, non-linear optimization, but the very famous are three categories. That is continuous optimization, discrete optimization, and the third one is mixed optimization. So having this, I would like to remind some very classical results, which believed to be the pivot point of optimization. That is discussed in a metric space. One stress theorem is a very famous theorem of optimization, which is developed, I'm not sure, in 80s. It's believed to be the turning point of optimization. What it is saying is this one. Let X be a metric space. F maps X to R. Here function. Then, if F is continuous and X is compact, then the minimum of F of X, this unconstrained optimization admits at least one solution. This is called the Weierstrass theorem, which says that F should be, we have this, F should be continuous, plus this should be compact. This implies that F admits the minimal, not only minimal, and the maximal form. It's maximal. F admits that it's maximal and minimal. Because this, the image of compact set under continuous mapping is compact, so it attains the minimum value and maximum value. This is for the Weierstrass theorem. So the problem was here, what was the natural question when this result was stated was how we can continuity and compactness. This was the research question which comes first, so that we can, the development of optimization rates here, starting from this one, how we can continuity and how we can this compactness. These two conditions are very strong conditions. So after this one, many research or results have been, many terms have been stated following this one. So the first one is continuity. The obvious one is weakening continuity is maybe assuming to be lower semi-continuous and upper semi-continuous. Then in practice, there is another point. So following this one, some terms have been introduced which are greater than this continuity concept. Let X be a net expense. And be a function. Then I would like to introduce some terms. We're going to some terms following this result. The domain of F is to mean that the set of points in X so that the value of F at X is finite. The domain of F is to mean this one because I'll use this. Second one is epigraph. Its epigraph of F is the set of points of alpha X, an element of this product space. So that alpha is greater than or equal to F of X. Third, hypograph. Hypograph of F is the set of points an element of R cross X. So that alpha is greater or equal to F of X. And maybe the third one is very important concept is for alpha an element of R, alpha sub-level set. Alpha sub-level set of F, which is usually denoted by this one. This is the set of all X in X. Tells that F of X, the value of the function of X, is less than or equal to something. These are very important terms for my next discussion. Alpha sub-level set. So it means that X is an element of the domain of F, if and only if F of X is less than or equal to alpha, meaning that, X must be an element of alpha sub-level set of F for some alpha an element of R. Meaning that domain of F is the intersection of alpha sub-level set of F where alpha runs the set of real numbers. This is very important. Alpha sub-level set is to mean this. If we have alpha here, the set of points in X is a functional value of F is less than this one, maybe here with this one. This is part of alpha sub-level set. And from here to here, this is alpha sub-level set. So the union of all this is union, sorry. The union of all this alpha sub-level set is dominant. But if you make, what will be the intersection? If we know that the infinite value of F, intersection of alpha sub-level set of F is obviously the set of all minimizer points. That is argument of F. So the intersection of the domain of F is the domain, the union is the domain. Now, I would like to state our semicontinuity and upper semicontinuity, which are weaker conditions than continuity.
Just a comment. We got some comments from the chat asking if we can write slightly bigger so they can see.
Oh, slightly bigger. Okay. Okay. Now, let me discuss the text of the metric space. F is a function. Then, when we say that a function F is non-semicontinuous, F is, this is a metric space. F is non-semicontinuous. And X left if the following condition is satisfied. If only if, then we make it X naught. Okay? The value of the function of X naught is less than or equal to the limit of f of X. X goes to X naught. What is this limit with? This limit is to mean that the supplement, the increment, when the increment is of n for X, an element of an open set without X naught, and the supplement value is an element of X naught neighborhood, X naught neighborhood of f of X. What is this set? This set is the set of all V, subset of X, so that X naught is in V, and V is open set. So, well, the definition is this one, which is a very beautiful definition of Fenchel. So the initial value of this function is this X naught neighborhood. Will be considered at f at X naught, so that over top over this instrument we find the supreme value is in this set. I will give examples so that we can consider this order. F is lower semicontinuous. In short, I will use this one. F is upper semicontinuous. It's minus of F is lower semicontinuous. So meaning that I can have this the value of F external is greater than or equal to lim sup of F of X goes to X naught. This is the increment, the supplement of F of X over X, an element of U, where X naught is deleted, and U is an element of X naught, where this is this one. So F is continuous if F is upper semi-continuous. X node in X. Of this X node in X. So F is continuous if it is upper semi-continuous and not just semi-continuous and then. So this continuity, upper semi-continuity and also we get conditions. We get conditions. Simple example is this one. Maybe we have this is minus x squared minus 1 with the value of, so that f of x is x squared plus 2 x is strictly divided by 0 and x equals 0 minus x squared minus 1 x is strictly divided by 0. So if we compute, we need that x goes at 0. Okay, let's compute at 0. Meaning that if you take the neighborhood of this one, consider this. So it will be that if you know this variable is less than or equal to -1. Anyways, if you manipulate this, if you manipulate this value is greater than or equal to -1. So the superior will be -1. That's all it. Because we can take any neighborhood. Over this neighborhood, the infinite value is here. Over this infinite value, the supremum value is -1. This is 2. -1. So meaning that F is lower semi-continuous at square. If f of a, f of 0 equals a should be less than or equal to 1. The value of a should be less than or equal to 1 to be lower semi-continuous. Let's look how f of x at x goes to 0 is 2. So meaning that f is upper semi-continuous at 0 if f of 0 a must be greater than or equal to 1. If this function is continuous, if these two are equal, but there is no instance. It's the negative aspect. -1 is greater than or equal to 2. Right? So this is a very simple example of also continuity definitions. So there is F is lower semi-continuous. If we say F is lower semi-continuous, it means that it is lower continuous and lower semi-continuous over whole space. We have the following here. F is lower semi-continuous if you know the steep plot. F is closed. Lower semi-continuous on the whole space. At each point in the space, at each point in X, I think that metric space. Oh, it will be closed. This is closed on the product space. Okay. On the product space, if that is defined, the subset of R cross the metric space. Metric space here under the metric used by this one, the topology used by this one. Closeness is checked under this one. Okay, under the product space. F is upper semi-continuous. Hypograph of F is closed. F is continuous. We can know if F is lower semi-continuous and upper semi-continuous. These are very important concepts relating lower semi-continuity with antigraph, upper semi-continuity with hypograph. So having this, I would like to state this theorem, which believed to be the next classical result of Weierstrass theorem. Let X be a metric space. Be a function. Then, if one, F is lower semi-continuous. Two, there exists X naught, an element of the domain of F, such that F of X naught sublevel state of F is compact. If these two conditions are satisfied, F is lower semi-continuous, and if you can find X naught in the domain of F, so that the F of X naught sublevel state of F is compact, then it is true that then the increment of F of X with the whole space X admits at least one solution. This is a very interesting result, which believed to be weaker than the Weierstrass theorem, or at least continuities here. Revised to be lower semi-continuous. This whole space is not compact here, so certain space. Just this need to be compact so that the optimization problem admits its solution. Now I use this as a very interesting concept. A very interesting concept. More debate. Go to the next concept, because in optimization problem, when considering optimization problem, basically three questions are natural questions. The first one is under what conditions the optimization problem admits the solution. Second one is if the solution exists, what is the characteristic of the solutions? And the third one is if you have solutions, how do you compute to find the solution of these optimization problems? So having this as an introduction, let me come to differentiability. So after this, my discussion will be reduced to a normal space, or in a metric space. So if we discuss about differentiability, first concept of differentiability which comes to our mind is context differentiability. Now is that context differentiability, so that let X in normal space. This is the function. Then F is convex differential. The whole X naught available X. X available of X. If the following two conditions are satisfied, if one presented this way, this value is this two. This exists as what? Exists as a real number. For all edge, this limit should exist as a point in a real set, in a real set. But it should exist for all edge, not only this one. This should be, this should be, this is a bounded linear operator from X into R. Should be this value should exist as a real number, and this should be the mapping which maps X into R. Should be an operator which maps X into R. And in fact, since we are considering real normal space, this means that this is a linear function, on the linear function. Meaning that this implies that there exists. Let me denote it this way. This is my notation. Okay, there exists such an operator. There exists this one, an element of bounded linear operator. Functional. Like that. This value for all inches. This is to mean that g of f of g of f of x. This is simply this one. Because why I use this is it's very important to use this one, because if we have x and y are normal spaces, let's have this from the set of all bounded linear operators on x to y, cos this is cos x y by this one. It's bounded linear operators for this. this one will be an element of this mapping is bifunction. It is linear in the first, and it is linear in the second. Okay, this is to mean that this is a bifunction. It is linear in the first, also it is linear in the second. This is because of the property of T. T is bounded linear. So that's why it is usual. It's important to state it this way. It's not before the actually. It's formally standard to be presented this way. Okay. So this is basically to mean that this value. So if such G of f exists, here G is called such exists. This operator is called the Getachew derivative. Getachew derivative of x. So this limit might exist. This limit might exist, but this is very important. If this exists, means that if this conditional only satisfied, then the directional derivative of the x is the direction of which exists. So you can say this. No, not a differential. It's not a differential. This is very important. If it is not a differential, x an element of x, then the Getachew derivative and computed on this one. It is a very simple competition. The Getachew derivative of x is the dt of this is obvious. If it is Getachew differential, this we know that Getachew differential with this simple competition we can find the Getachew derivative. Getachew derivative. Second one is if it is Getachew differential. This is very important because I will have very stronger differentiability later. Differentiability. This will be very important in linking Getachew differentiability with Fenchel. This is zero. If it is Getachew differential, this limit is zero. This is very important later when we have a relation between Getachew and Fenchel. I would like to give an example of this. I like examples. I like examples. Very very long one is let this be open subset of R. And consider this. The space X the level space. Let us functions that we have on this set and integral functions. This set, let's have a function. This obvious is a normal function. So for this function, what is surprising is for this function, the graphics derivative of f at x is t times absolute value of x, t minus 2, t minus 1, I of x. Very important. Actually, we can eliminate this times of x and eliminate this. So we can have this. The graphics derivative of this function is this one. What is true behind this is also the graphics derivative of f at x is an element of true, but it is one space, one of the elliptic space, and the one of the elliptic space is LQ space, where Q is a conjugate. Q is an element of R with 1 over P plus 1 over Q is 1. This is the analysis. Usually, this one is analysis. Next one express with P equals 2. P equals 2. The dual of this was a especially in Bayesian training for real analysis. The graphics derivative, might be the directional derivative of x might exist, but it might not be Gaussian differential. The obvious example is this. This function. Here, if we complete this 0, let's see. Let's complete at 0. 0 plus h. 0. H is 0. This is h is 0. It's 0. H is not 0. So this we have this t equals or 5 1 square cube h1 squared plus this limit existed, but it is not here. It's not linear. If it is linear, it's bounded in a finite dimensional space. Show it is bounded. Linearity is enough. Even it's not linear. So the first condition is satisfied, but second condition is, but this is not linear. So this is, but it's not convex differential. Not linear. The first condition is that here is satisfied.
It is not, right?
It is not, sorry. It's not convex differential. Now we'll see very stronger differentiability condition called Fenchel differentiability. So it is convex. Actually, we have, let me state, sorry here, let me state the general case of this. X, the image should not always be real. You can have Getachew differential T for a mapping from normal space to a normal space. Normal space. That is Getachew differential. Not an element of X, one definition now. We bring this limit in this one. If the limit of f of x plus h minus f of x exists and equal in what? For all h element of x should exist, and this very much will exist at the point in what? Second one is there exists, let me say, there exists the bounded linear operator from x to y such that this is this one. So that is differentiability can be generalized from only grade one functions. So we can have also this one. We can have from other quadrants. We can have plenty of examples. If it is linear, definitely will be Getachew differential. Now, it is a right moment to define Getachew derivative. Fenchel derivative. It's to be a normal space. And f is a function of x, the function. Right. F is Fenchel differential. If there exists this, if you can find, then you have also in my own representation. I use G for representing the vertex. I use F here, which is if you can find this one, which is bounded linear function, bounded linear function, set that. The limit of f of x plus h minus f of x minus this value of h over normal h. This norm is completed normal is with x, where this normal goes to 0. This should be 0. If you can find such a mapping so that this limit is 0, then we say that it is differential. In this case, if this exists, this operator for the Fenchel derivative sorry, F, big F, big F. Where in the sense of H. Thank you so much. Well, in the sense of Fenchel, if you can find so that this limit is this limit is 0. So this is very solid. We have set of convex differentiable functions. We have set of Fenchel differentiable functions. Fenchel differentiability is convex differentiability, but the reverse is not true. This is not true. Fenchel differentiability is given by indirect composition, but convex, as you can see, you can obtain it by direct composition. It's given directly, but this is indirect. Fenchel is convex. If we know that the function is Fenchel differentiable, so we don't need to use this condition because that Fenchel differentiability is convex. So we can use the convex derivative to be computed using this one. Derivative to be computed in this one. What is very important reason here is Fenchel differentiability implies convex. But the converse is not true. One very simple example of this is I can have this to be this one. If x1 but scope means it's equal from 0 as always. Okay. X, here we have X. Denominator we have T. Here we have T to make this zeros. This is 0, this is 0. And this matrix, but if you compete, if you try this, if you try this, but it takes me time, try to use this, find abstracted differentiability. So there is no, you cannot find the mapping of this so that this limit gives 0. But this is not, it's a very simple combination, but it's not. That is not Fenchel differentiable at 0. That is not Fenchel differentiable at 0. This is the difference. The difference. Okay, we have plenty of examples where the function certain mapping is matrix differentiable. And then the function is not Fenchel differentiable. This is always example. We can also extend Fenchel differentiability for the normal space to a normal space. We have this Fenchel differential. It's unavailable. If there is a mapping based on X, bounded linear operation X to Y, exert the limit of f of x plus h minus x minus the this norm is in Y. Okay. This is because real value. Over this one. If such a mapping exists, the limit is equal to 0. And if this differential affects this value, the Fenchel derivative. Why I forgot here is just to make it simple, show that this function is not Fenchel differentiable. Counter example, maybe to make HL to be this one. This is a point in R2 which converges to 0. If you use this with this sequence points, you cannot have to be this, cannot get this limit to 0. You cannot. Even with 2 steps, it will show you that you cannot have. So let me discuss the property of convex and project. First one is maybe let's x and y in normal spaces. And let's have only x and y. Let's have x, y, and z. These 3 normal spaces. Where the marking from x to y in convex differentiable. X to x. And g from y to z. Richard, that's there. F of x. Okay. Its value is in y. Then the composite function in Getachew differentiable latex. G of f of x x, and the convex derivative is given by this. This mathematical chain rule. Okay. That's the chain rule. The convex derivative of f at x. This one. This is obviously the composite at x. The convex derivative of g of at x is the convex derivative of g at f of x composite with the convex derivative of f at x. The convex derivative is given by this. This is the chain rule. Is simple like that. The convex derivative of f in the direction of h is given by the convex derivative of f of x of g of. We can complete this. So come to the next properties of convex differentiability. It's better if I remind the definition of convexity, strict convexity, and strong convexity. the function, then F is convex. Just to remind you, if F of alpha x plus 1 minus alpha y, the laser is constant for alpha times F of x plus 1 minus alpha or F of y, or all x and y are minimum x, and alpha should be a minimum of. This is strict convexity is strictly less than 0 for two distinct points. Distinct points. Strictly convex. Strictly less than. With third one is alpha is strongly convex. Maybe for alpha, remember, it's beta strongly convex. If f of alpha is 1 minus alpha 1 greater than or equals alpha times x plus 1 minus alpha of 5 minus alpha times 1 minus alpha times beta with this one. This is comment that is probably convex. Comment that f of x minus beta over 2 of norm of x is convex. This is convex, then the function is strongly convex. Given the form of this one, if this is convex, then f is strongly convex. Beta strongly convex function is constant beta. It's constant beta. Now, under this concept, we have the following three beautiful results regarding this convexity, strict convexity, strongly convexity with matrix differentiability. Is the open convex subset. Open convex subset of X. We see the open subset of X. If F is not X, matrix differentiability on C, then the following are equivalent. On C, meaning that the limit this exists for each x in C. This exists C is, so we are not concerned with this H is the whole space. Okay, this definition, not confused with this. So the following three equivalent results are very important for Mike's Morrow's discussion. The following are equivalent. One, F is convex. Two, the matrix derivative of the matrix at y minus 6 is literally equals to f of y. X. Very important. Later when discuss about subdifferentiation or commit differential is differentiability. Third, the property is this. These three are equivalent. So I don't need to write another statement. If it is strictly complex, this will be strict. F is strictly convex. Okay. If it is strictly convex, this will be strict. And here for x, y is seen with distinct points. That is strictly convex. This is always division. Its condition will x from two distinct points. This is also strictly greater than 0. What we'll add here is all x and y will see with different y. If it's strictly convex, this three equivalence will hold. The next three equivalent statements are this. It is strongly convex. It is strongly convex. The convex is related with convex with y minus x minus beta over 2. Actually, in finite dimensional space, this is the formal definition of strong convex. Formal definition. Here, this reverts to finite since it is reflected. This can be represented as a single element of the space itself. That's what it's very simple. The target derivative at a point x minus 1 greater than or equals times this is very important among our related matrix differentiability with the differential are very important concepts. So having this discussion, I would like to close this lecture by stating one first order condition of optimization with regard to this matrix differentiability. Then I'll end here at this term. This is called the first order condition. Optimality condition.
Who is over there in the lower three?
That's the normal space. And for a real Boolean function. Okay. If convex differentiable at the point x bar by x, and x bar is the minimizer point of f. Then if we complete the matrix derivative of f x bar is 0, that is 0 means that 0 nothing. That is derivative, so 0 nothing. This is very interesting. Very easy. Maybe. Since f is Getachew differentiable, and if x is the minimizer point, x is the minimizer in that, bar is the minimizer point. Zero is less than or equals to f of y minus f of xy. So it's less than or equals to xy, less than or equals to y. This is true. So basically, like that, if this holds for all, zero is less than or equals to x bar plus h minus x bar for all x and direct consequence, because this is an element of x. So this implies that over t, and giving it limit, 0 is less than or equals to the limit of we give it than 0 for all h. This is obviously finish it here. But limited, nothing derivative of f. On this one. Also, Gatex, if there is Gatex derivative from this limit existed, then Gatex derivative. It's the limit is valid. So if this is true, we have to start here. You think like that? Minus of which. Because this is linear. Linear. There is so many qualities. And it's very good. Found the linear operator, ups every point zero. This operator is zero. Zero. At the end of this, continue to on quality, which is quality expression.
Stop the recording.